At last, we have reached this last video of the AP Calculus review series, specifically for BC students. For AB, it was Unit 8, but this is Unit 10, Infinite Sequences in Series, and it's going to be the last unit of Calculus. And so, with this video, you're basically done with your Calculus journey, and the only thing left is to wish you good luck for your exam. And we're not done yet, though, because we still have this unit to do, and it's a relatively long one. Not as long as the applications of integration or the integration unit itself, but this one's up there. And so with that in mind, let's just get started with the content review. And so starting title, it says infinite sequences in series. What is an infinite sequence or series? Sequence is just a set of terms, and so an infinite sequence is an infinite set of terms. We're mainly talking about infinite series, though. And that is a sum of infinite terms that follows a certain pattern. For example, 1 plus a half plus a fourth plus an eighth. Do you see the pattern here? And so on, all the way to infinity. That's why it's called an infinite series. This is actually a pretty famous example. You should know how to calculate this from algebra and pre-calculus. But we will talk about how to calculate this in a minute. First, there are three types of series. First, a convergent series has a limit, has a finite limit of partial sums. If you take the limit of the partial sums, which is just, this is the first partial sum, second, third, and fourth. If the limit as n approaches infinity of this partial sum is finite, basically it exists, then it's convergent. If it doesn't exist, it's divergent. Basically, the limit of partial sums is infinite. And then the third type doesn't really have to do with any of these, but an alternating series is when the terms alternate between positive and negative. You can have 1 minus a half plus a fourth minus an eighth and so on. You're alternating between positive and negative, and that's an alternating series. And so you might know all this from algebra or pre-calculus. I'm doubtful you know what convergent and divergent series, or at least the formal definition of them are. But you should, it's kind of intuitive here. But what you don't know definitely are the tests that you use for these different series. There's a bunch of them, a handful of them. And now when you're given a series, usually in summation notation like this, you can find out whether it's convergent or divergent using a bunch of tests. And you're going to just use one of these tests on each series, but the hard part is deciding what test to use. And then after that is remembering what the different tests are and then actually using the test. And so let's run through all the tests one by one. First is the nth term test. And that basically says that if the limit as n approaches infinity of the sequence itself of a of n is not equal to 0, then it diverges. This is one of the only tests that actually say it diverges as a conclusion. Most of them say it converges as a conclusion, but this one it says it diverges. But that doesn't mean that if the limit as n approaches infinity is 0, that means it converges. It's possible that it still diverges if the limit is equal to 0, but if it's not equal to 0, then you know for sure that it diverges. So that's the nth term test, also known as the divergence test. And just to conserve space, I'm going to be erasing the test after I'm done explaining about it. I'm just going to keep the list of tests up on the screen. Then there's geometric series. This that I started talking about earlier is actually a geometric series. A geometric series has a common ratio r, and if this r is less than 1, then it converges. This, you say it converges if it's less than 1. And so an r of, a negative r that's less than negative 1 also converges. So the absolute value of r has to be less than 1. The third one is alternating series. And we did talk about alternating series just a few minutes ago. If the alternating series has a limit as n approaches infinity of the absolute value of a of n. Absolute value, that means you don't care if it alternates anymore, it's just the magnitude of the term. If that is equal to 0, then you know for sure it converges. It's similar to the nth term, but more powerful, because if it's alternating and the limit as the term approaches 0, then you know for sure it converges. It kind of looks like that. It's converging to a certain value. Okay, well, what about the next test? P-series. P-series basically says if you have a series in the form of 1 over x to the power of p, for example, or n to the power of p or whatever, probably n to the power of p is better because we are going to use x for something else. N is usually the variable we use. This converges if p is greater than 1. If it's less than or equal to 1, it diverges. And so now we have enough information to answer this. This one has n to the power of 1, and so p is less than or equal to 1, which means it diverges. It still approaches 0. Limit as n approaches infinity of 1 over n is equal to 0, which actually kind of proves what I was saying about the nth term test. Because just because it approaches 0 doesn't mean it is convergent. But if it doesn't approach 0, then you know for sure it's not convergent. So yeah, you can use the p-series for something like that. Okay, fifth test. This is just the first 4 out of like 8 of them. This one's called the direct comparison test. And basically what it is you have a known series. You know if it converges or diverges. And you have this unknown series that you want to see if it converges or diverges. If this unknown series is less than or equal to the known series, and the known series converges, then the unknown series converges. Similarly, if this unknown series is greater than or equal to this known series, and the known series diverges, then the unknown series also diverges. Another way you can say, if a series is less than a converging series or greater than a diverging series, then it has the same convergence as that other series. This is pretty useful because if you know that 1 over n diverges, for example, and 1 over n minus 1 is always going to be greater than or equal to 1 over n, because you can plug in a few terms and see that 1/3 is greater than or equal to 1/4, for example. That means 1 over n minus 1 also diverges. Okay, but what if you have 1 over n plus 1? Well, that's less than or equal to 1 over n, but 1 over n diverges, so we can now use the direct comparison. So we have to use its cousin, the limit comparison test. And the only reason I'm calling it its cousin and not its brother, for example, is because it has the same name, but it's not that similar. All it does is it compares two series, but it uses a different method. Direct comparison is just inequalities. Limit comparison, you take the limit, as the name suggests. If the limit as n approaches infinity of the quotient or ratio of these two terms is finite but not 0. So if it's 0 or infinity, then it's inconclusive. But if it's finite, then it has the same convergence as the known series. So let's try that with this example over here that I was just talking about. Here we can use the limit comparison test. So you do limit as n approaches infinity of 1 over n over 1 over n plus 1. And so if you were to simplify that, that's just limit as n approaches infinity of, well, this is just n plus 1 over n because you're swapping the denominators when you're simplifying the complex fractions. And so this is equal to 1, and that is finite but not 0. And so it has the same convergence. The original series diverges, and so this also diverges. And so you can use limit or direct comparison tests when they're pretty similar, but sometimes direct comparison doesn't work. Note that if it's 1 over n minus 1, you can also use limit comparison. You just cannot use direct for 1 over n plus 1. Limit is just a bit more powerful than direct, I would say. And then the 7th test, the integral test. Here we're getting back into our calculus roots. We're talking about integrals. We have actually diverged, no pun intended, from calculus a bit. We've been talking about how to find if series are convergent or divergent. We have talked about limits and things like that, but no, we haven't talked about derivatives or integrals in a while. And finally, here we are, integrals. It says that if it's a continuous positive decreasing series, all three of those conditions have to be met, and usually they will be, but always make sure to check. Continuous, positive, decreasing. And you have the summation of that series a of n, then it has the same convergence as the improper integral with the same bounds. So let's say this is k equals 0 to infinity, right? Or n equals 0 to infinity. It's going to be 0 to infinity of f of n. That has the same exact thing. So if this is 1 over n, for example, this would be 1 over x dx. Would be the improper integral. You calculate that. If it converges, then this also converges. If that diverges, then the series also diverges. Now notice if this converges to a specific value, like 1, it doesn't, obviously. This is just an example. That doesn't mean that the series itself converges to 1. It just means that it converges. Important distinction to make over there. And then finally, most powerful test, I would say, is the ratio test. You're going to use it a lot in the second part of this unit, which is about power series and things like that. It says with power series, this is called the ratio test. Sorry about that. If limit as n approaches infinity of the next term over the current term is less than 1, then it converges. If it's equal to 1, it's inconclusive. If it's greater than 1, it diverges. And so you're going to need to kind of use this a lot when we're getting into the next topic. But usually you use this when you have a bunch of n's, like n in the exponent, n factorial, things like that. It's easy to cancel off with the next term. So those are the 8 tests you should know. Know how to use, know when to use, and things like that. Okay, one more thing about this. Absolute convergence is when if the series absolute value of a of n converges, then the series a of n also converges. You know this for a fact. If the absolute value of a of n converges, then just a of n converges as well. And so if a of n is an alternating series, you can take the absolute value of it, see if that converges, and if so, then this converges as well. You can prove that easily with the nth term test, by the way. And so in light of this, you can describe a series in 3 different ways. First, converges absolutely, which means that both of these converge. Converges conditionally, which means that only the alternating series converges, but the absolute value does not converge. And then diverges, which means both of them diverge. And I can give a few examples of both of them, of all 3 of them. If you have -1 to the power of n over n squared, this is absolutely converges, because this converges because when you use the alternating series test, it approaches 0, which means it automatically converges. If you take the absolute value of it, you get 1 over n squared, which by the p series test also converges. But if you were to remove this 2 here, you would get -1 to the power of n over n, which does converge by the nth term, by the alternating series test, because the limit approaches 0. But when you take the absolute value of it, you get 1 over n, which we also already proved diverges because of the p series test. And then you can find a bunch of examples of series that diverge just without conditionally converging. For example, -1 to the power of n just times n. You automatically know this is going to diverge because it doesn't even satisfy the alternating series test, where the limit as n approaches to infinity of this approaches infinity, because there's this n here instead of in the denominator. So good thing to know, absolute convergence. Okay, finally, the second part of this unit. We talked about tests and how to use them. Now we're going to talk about power series, Taylor polynomials, Maclaurin polynomials, error bounds, fun stuff like that. We're getting back into calculus. Not yet, actually. Power series is not strictly calculus, but it's basically when you have x in there. You have some series, a of n, and then you have this x minus c to the power of n term. And so an example would be x minus 2 to the power of n over n factorial. This is a power series, where 1 over n factorial is this other series, a of n, that you're multiplying by, and here x minus 2 to the power of n is x minus c to the power of n. And you can expand a few terms, do some stuff with this. But what we're mainly going to do is find the interval and radius of convergence. So the interval of convergence is basically the interval for which power series converge, and the radius is half of that interval. And usually when you're determining the interval of convergence, you use the ratio test because most of the examples, which is going to be like the series of x minus 2 to the power of n over n factorial, it has an n factorial. Ratio test is pretty useful here. You can do next term minus current over current term, limit of that, and then see what that's equal to. And usually it's going to be less than 1. Or no, you set it less than 1 and solve for x when it's like that. And so, quick example of that, if you were to use the ratio test, limit as n approaches infinity of this, I'm just doing an example because it's a pretty important topic. You do n plus 1 over n plus 1 factorial, and then since you're dividing by a fraction, you're multiplying by its reciprocal, which is just n factorial over x minus 2 to the power of n, and things cancel out. You get limit as n approaches infinity of x minus 2, because that cancels out with that, over n plus 1. And you want this to be less than 1, because you're trying to find out where it converges. And so this, just 1 over n plus 1 always is less than 1. And so you want this is just limit as n approaches infinity of x minus 2 times 1 over n plus 1. This approaches 0. And so you have absolute value of x minus 2 just by itself is less than 1. And actually, in this case, it's not going to be less than 1. This just converges for all values because this approaches 0, which means this entire expression approaches 0, which is less than 1. So this is a bad example for a power series, to be honest. But if it was something like n over n plus 1, you somehow got that as the limit. You would do this approaches 1, and so all that's left is this absolute value of x plus 2, which is less than 1. And so now you solve this inequality for x. It's an absolute value of inequality which you should know how to solve from algebra. And so negative 1 is less than x minus 2 is less than 1. And so you can solve for x by adding 2 to both sides. You get 1 is less than x is less than 3. But we are not done. The interval is 1 to 3, but what is it, closed or open? And so you test the endpoints by plugging in 1 into this. If you plug in 1 into this, you get 1 minus 2 is negative 1 to the power of n. And so you have a series negative 1 to the power of n over n factorial. Does that converge? Yes, it does by alternating series test. And so this is closed here. And obviously, again, I made an edit to here. So we're not plugging it into the actual series that gave us this interval. This is just an example. I should have chosen a better example in hindsight, but this is how you would do it. You would solve for the interval, and then you would plug in the endpoints back into the original series to see if x equals this certain value, will the entire series converge or not. So that's just how to use power series in a nutshell. But we can apply power series to a much more interesting topic, and that is polynomials. We're going to approximate polynomials using what are called Taylor and Maclaurin series. Now, ding, ding, ding. Remember I told you way back when, probably in unit 4, about how a bunch of calculus was about approximating things, approximating values of functions, using tangent lines, then using Euler's method. Now we're going to be talking about Taylor polynomials to approximate functions. This is going to be the best method we've done so far, which is why we're learning it last. And so how do you construct a Taylor polynomial? It's just using the nth derivative of a certain function. So f of x is equal to the series of, and this is going to get complicated pretty fast. So it's the nth derivative at a point a over n factorial times x minus a to the power of n. And this is a power series. This is, no matter how weird it looks, it's all in terms of n, and then there's this x term, meaning it is a power series. A here is the point you're centering it around. This is a Taylor polynomial with infinite terms. But if you wanted a finite one, without using this, you would just use the nth derivative of a function. So if you have x cubed plus 3, this is actually a bad example because that is a polynomial itself. Let's say you have sine of x, right? You would construct the Taylor polynomial by saying, well, what is sine of, let's say we're centering it around 1, or pi. Pi is easier. Sine of pi, well, that's just going to be equal to 0. And so this is 0 plus, and then you plug in, what's the derivative of sine? That's going to be cosine. Cosine of pi is negative 1. And so you do negative 1 times x minus pi to the power of 1 over 1 factorial. And so it's basically going to be this exact formula. You just are doing it for a finite polynomial instead of an infinite series. And so you can find like the first 3 terms by just plugging in the third derivative, third derivative of the function, and then x minus a to the power of 3 over 3 factorial, and so on. So that's how you would calculate the Taylor polynomial. Maclaurin polynomials are a specific type of Taylor polynomials that are centered at x equals 0, and they're much easier to solve for. That's going to be equal to the series of f n, the nth derivative at 0, over n factorial times just x to the power of n, because a is 0 in this case. And so that's going to be your Maclaurin series. And so I'm kind of speeding through this because this is just a content review, and it's already going pretty long, longer than I expected. And so these are the 2 types of series that you should know how to construct from a given function. But there are also a few you should memorize. If it's e to the x, that's equal to the series x to the power of n over n factorial. If it is cosine of x, that is equal to this is a bit more complicated, negative 1 to the power of n. It is alternating, times x to the power of 2n over 2n factorial. This is cosine. Sine, that's going to be pretty similar. It's going to be negative 1 to the power of n times x to the power of 2n plus 1 over 2n plus 1 factorial. And then we have 1 over 1 minus x, which is just the series of just x to the power of n. Very simple. And so you might be wondering, why do we need this weird function? Well, that's because it just gives us a really nice Maclaurin series. And that's not all. Using these four, you can use substitution, differentiation, and integration to calculate others. For example, how do you find inverse tangent of x? Well, you know that inverse tangent of x plus c, technically, is equal to the antiderivative of 1 over 1 plus x squared, for example, dx. And so what do you do there? Well, using this, you can plug in x is equal to negative x squared. That looks really weird from a mathematical standpoint, but we're just plugging in x into here. So 1 over 1 minus negative x squared, which is just equal to 1 plus x squared, which is what we want. So we can find the Taylor's or the Maclaurin series for 1 over 1 plus x squared by just plugging in negative x squared wherever we see an x in here. And then we take the antiderivative of that resulting polynomial, and we're going to get the Taylor or Maclaurin series for inverse tangent of x. And finally, error bounds. So you have all these nice formulas. How do you find out how accurate they are? And so there are two types, one for alternating series and one for just general functions. So you can use alternating series with cosine and sine, and you would use Lagrange, for example, with e to the power of x. I also erased 1 over 1 minus x because the only purpose that served was for the inverse tangent derivation. You still should memorize it, but it's not as important as the others. It's also it's kind of easy to derive. Okay, so yeah, alternating series error bound. So if you have a function f, the actual value of f of c minus the Taylor polynomial at c, the absolute value of that's just going to be the error. The maximum value of that error is going to be equal to the absolute value of the n plus first derivative at c over n plus 1 factorial times c minus a to the power of n plus 1. And so a is where you're centering the Taylor series around, or Taylor polynomial. Taylor series are always exactly accurate. Taylor polynomials are the finite representations of Taylor series, and so they are not always accurate. And so at a certain nth term, let's say you're doing a 4th degree Taylor polynomial, you do the 5th derivative, and then you do 5 factorial down here to the power of 5 here, and so on. That's for alternating. This is just going to be the next term of the alternating series, just the absolute value of the next term. Because as you can see, this is what you do. Well, technically this one for centered around a, and so that's just exactly the same thing, but you just plug in n plus 1 instead of n, and c instead of a, because you're plugging it at a certain point. That is not what you're centering around. And there's Lagrange error bound, which if it's not alternating, you use this. This time it's less than or equal to, and it's m over n plus 1 factorial times c minus a to the power of n plus 1. And that looks very similar, but you see this big m here. What is m? And so it is going to be very similar to this term, the n plus first derivative at c. But usually alternating series are kind of easy here because you're just plugging in the next term, and so you don't really usually need to calculate this. You just find the next term by plugging it into the Taylor polynomial. They'll usually give you an extra term and then ask you, let's say they give you a 5th degree polynomial, they ask you what's the error for the first 4 terms. You just plug it into the 5th, so you don't really need to do anything. But for Lagrange error, it's not going to be the next term, and so what you're going to need to do is find the n plus first derivative, which can be pretty hard. And so especially since you're going to do this without a calculator most of the time, since the entire point of approximating functions is doing it without a calculator. And so how are you supposed to find the value of the n plus first derivative without a calculator? Well, that's why m is the maximum value of the n plus first derivative on a certain interval. So let's say it's from 0 to 1. It could be 1, but let's say it's something like e, right? You don't know the exact value of e to the power of 1. You might, obviously. Maybe it's like e to the power of 0.5, for example. You don't know the exact value of that. But you can say e to the power of 1 is less than 3, definitely. Because this, to be honest, is 2.7 approximately, 2.718. But you know it's going to be less than 3. And so you say m is equal to 3 and then plug that into. So you're just making a conservative estimate for this error. It's usually going to be less than that, but sometimes you have the exact value of the function and you can just plug that into m. Okay, And yeah, that is it for a content review. It took way longer than I expected, but that is a pretty thorough explanation of Unit 10. It's time for our practice problems. We have 4 this time. The first 2 are both testing a series for convergence, which is a pretty big chunk of this unit, to be honest. So let's start with the first one. We could use ratio test, for example. Let's try that out. Limit as n approaches infinity of the next term, which is n plus 1 over technically n plus 2 to the power of n plus 1, because n plus 1 plus 1 is n plus 2, times reciprocal, which is n plus 1 to the power of n over n. And that's pretty hard to evaluate. But what we do see is an n to the power of n times a n, which means it's approximately n to the power of n plus 1. There are other terms that follow it, but all we care about is the leading term when we're talking about limit as n approaches infinity. Here, we have n to the power of n plus 1 times an n, which gives us n to the power of n plus 2, which simplifies down to 1 over n. And so you can say that this limit is equal to 0 because of this. It's kind of hard to show, but it is valid. If you can somehow explain it on the AP test, you can use this, or you can try using other tests as well. And so this is less than 1, and so this is a convergent convergence series based on the ratio test. Okay, this second one. Okay, technically we can say that this first one converges absolutely, because even though this is not an alternating series, absolute convergence is not limited to alternating series. It just, we usually associate them with it because we see an absolute value there. And so technically the absolute value of this is it itself, and so both of them do converge, meaning it does converge absolutely. We can say that here. Here, it also, it makes even more sense to use absolute convergence. So we will try that. We will see if it converges absolutely, conditionally, or diverges. For this one, we can use the alternating series test, limit as n approaches infinity of absolute value of this, which cancels out the alternator. So n plus 1 over 7 n squared minus 5. We see an n and an n squared here, which means this does equal 0, and so it does converge. So we see this converges, but does it converge absolutely? Let's take the absolute value of it. So into a series of n plus 1 over 7n squared minus 5. Does this converge or not? One way to figure it out is limit comparison test, because we see an n and n squared, so it's like having a 1 over n, which we know diverges. But let's see if this is similar to that using the limit comparison test. And so limit as n approaches infinity of n plus 1 over 7n squared minus 5. And so we're dividing by a fraction, meaning multiplying by a reciprocal of n over 1, which is equal to limit as n approaches infinity of n squared plus n over 7n squared minus 5. And so you know that's going to be equal to 1/7, because n squared, 7n squared is the ratio of the first terms, which is a finite number that is not equal to 0. And so it does have the same convergence as 1 over n. And so this one diverges, meaning this converges conditionally only. Okay, what about this next one? It doesn't give us any instructions, but the instructions for this problem should be find the Maclaurin series of this. We actually kind of did this. I didn't show you what it should be, but we know how to do it. And so we know 1 over 1 minus x is equal to this, right? Which you can also write as 1 plus x squared plus x cubed plus dot dot dot. And so 1 over 1 plus x squared is going to be using substitution. You say x is equal to negative x squared. And so every time you see an x here, you're going to replace it with negative x squared to the power of n. And so it's going to be negative 1 to the power of n times x to the power of 2n. And so this is going to become an alternating series now. So that's going to be approximately 1 minus x squared plus x to the power of 4 minus x to the power of 6 plus and so on. So that's going to be our Maclaurin series for this function. Okay, and this last one has to do with error. This is an alternating series, which means we can use the alternating series error bound. It says it's approximated by s of 50, so we use the 51st term. We can just directly plug in s51 into this, because the sum, this technically is not a Maclaurin series or a Taylor series or a Taylor polynomial or anything like that. It's just the sum of a series, and you can still use error for that. the sum of a series is just going to be equal to the value of a function. But this one isn't explicitly about a function. You can still use error for that. Usually it's not common, but it is possible. And so the sum of the first 50 terms of this series is approximately equal to the entire term, and the error of that is going to be the maximum error of that is going to be the 51st term. And so we just plug in 51 into here, negative 1 to the power of 51 minus 1 over 2 times 51 minus 1. So negative 1 to the power of 50 over 102 minus 1, which is 101. So that cancels out that. And it's also going to be the absolute value. And so even if it wasn't negative 1 in the numerator, it would be the absolute value of that, which is just 1. And so 1 over 101 is going to be the maximum error. That doesn't say it is the error, it's going to be the maximum error. The error is always going to be less than this value. And unfortunately, that is it for AP Calculus, all of the units. This is the last video, like I said in the beginning. But yeah, and so good luck on your AP test. Hopefully all this practice helped you out, but always seek more practice, do more worksheets, learn more content. This is just to refresh your minds and give you a taste of what is coming on the AP exam. So yeah, good luck on the AP exam, and I'll probably see you in another video.